Hello, this is Mrs. Hedden. I'm going to look at the WebAssign problems from that first grouping in Chapter 13. In particular, I'm going to look at 6b and number 8. Before we do 6b, let's quickly do 6a, which I have up here. What is a gauge pressure in a 26 degrees centigrade car tire containing 3.1 moles of gas in a 25.5 liter volume? And it gives you what value to use for R. So, like all times, I start out by writing what I'm hunting for and what I know. Eventually, I need to get the gauge pressure, and I've got the temperature. It's in 20 degrees C, so right away I change it to degrees Kelvin using 299.15 Kelvin. It's already in moles, and it's already in liters. What they told me to use for R has things in liters, so I'm going to keep it that way. Why do more work than I have to? I found their convention of writing the units a little bit confusing, so I double-checked in the book to make sure what the units were for that value of R, and I rewrote it like that. So here's PV equals nRT, solved it for P, and I put all the units in because I want to make sure they all cancel. And I've got moles on top and moles on the bottom, Kelvin on top, Kelvin on the bottom. Liters on the bottom here, liters on top, and that leaves me with atmospheres. So I know my answer is going to end up being atmospheres. And I work it out, and keeping everything in place, I get 2.98575 atmospheres. Remembering that that's absolute, I just take one atmosphere away and then round it to sig figs, and I get 1.99 atmospheres. Double check my answer because I got to copy it with the answer in place, and that's good. So I'm looking good there. Now I've got to look at part B. So part B is, what will its gauge pressure be if you add 1 liter of gas, originally atmospheric pressure, and originally at 26.0 degrees C? And then they've got this little thing where they say, assume the temperature returns to 26 degrees C and the volume remains constant. So you're adding 1 liter of gas to the tire, but the tire's volume stays at 25.5 liters. So what are you really asking for? Well, you're asking how much gas are you adding? And you've got to figure that out before you can figure out what the new gauge pressure is. So it's not really a volume addition because the volume is returned back to 25.5 in this problem. Okay, the original volume stays constant. So the real question I'm asking is, how many moles of gas do I now have? It's no longer 3.1. It's changed. So in order to figure out how many moles of gas I now have, I'm figuring out how many moles of gas I've added. And I'm just going to use PV equals nRT again, but this time I'm solving for N, the number of moles. And originally that 1 liter was at 1 atmosphere, and originally it was 1 liter in volume, and originally it was 26 degrees C, which is 29.15 Kelvin, and of course I'm using this R. Once again, I want to double check those units because I'm not real comfortable. I want to make sure they're all good. I've got atmospheres on the top, atmospheres on the bottom. Liters on top, liters on the bottom. Kelvin cancels out with Kelvin. Means I'm going to have a mole. That's an inverse fraction, so it means the answer is going to end up being moles. Sorry, it's not inverse, it's a complex fraction. So I've got 1 over moles. And multiply top and bottom by moles. And this will cancel out, and my answer will end up being in moles, which is what I want. And sure enough, I do all the math, and I get 0.0407 moles. So I'm going to add an additional amount of gas in moles. So now I go back to my original problem. Everything's the same, except instead of 3.1 moles, I've added that additional amount. So I now have 3.1407. Now, I left it complete in my calculator. It's actually a longer number than that, but I want to leave it complete until the very end and then round my numbers. Plugged it all into the equation. Again, double check my units. Kelvin cancels out with Kelvin. Moles cancel out with moles. Liters cancel out with liters. I'm going to end up with pressure in atmosphere, and I end up with 3.02496 atmospheres absolute. I want to get it to gauge pressure, so I'm going to take off 1 atmosphere. and I'm rounding. This 4 is below 5, so it's going to round to 3.02, or after I take off the 1 atmosphere to make it gauge, 2.02 atmospheres. I go back up and double check, and sure enough, 2.02 atmospheres. I'm in good shape. So that just leaves problem number 8. If you are fine with 8, you can stop listening now. Okay, I'm looking at problem number 8. The Goodyear blimp we usually see hovering above our heads contains so much glass, at so much of a mass, at so much of a pressure, and it wants to know what the temperature. So as before, I wrote down what I know, the volume, the mass, the pressure, and the temperature. And with that kind of information, plus with the chapter I'm on, I'm thinking I really want to use PV equals nRT. I've got 2 forms of it, PV equals nRT, where N stands for the number of moles, or PV equals nKT, where N stands for the number of particles. I don't have a number of moles nor a number of particles in this. But I can get the number of moles because I have a mass, and I have a relationship between mass and moles. So I'm going to go ahead and do that. I've got 1040 kilograms. And originally I have 4.026 grams per mole. So I've got to change that to kilograms, or else change this to grams, either way. So I'm going to change this to kilograms per mole, and I get that many moles, which is a large number. The best thing to do is to keep it in the calculator. I wrote it out for you guys, but I would also just keep that thing stored in my calculator. So now the next thing is I want to rearrange this equation. I'm going to use that, but what value do I use for R? I'm looking at the advanced placement constant and conversion factor sheet, and they've got the universal gas constant, R, is equal to 8.31 joules over moles times Kelvin. This guy in joules. Joules is the unit of energy. Energy, or think of a work. Work is force times distance. That's newtons times meters. And newtons we can put in meters per second and all that stuff. But basically going up here, we've got this in meters. We've got a Pascal. Pascal is equal to newtons over meters squared. So unless we want to convert our volume and our pressure, we're better off just using that universal gas constant of 8.31. So I'm going to go ahead and plug that in and do it. Okay, so I've got all my math down. I worked out the numbers. It's 285.29 Kelvin. I'm going to go back and check my units. So I've got a meter squared here and a meters cubed. So it's going to leave me with a meter on top. I changed this joules up here to a Newton meter down here, just to make it easier to do cancellations. So I've got Newton meters here. So this Newton is going to cancel out with this Newton. This meter, the one left over, is going to cancel out with this one. This moles is going to cancel out with this moles. And I've got a complex fraction. I've got 1 over K. So to simplify that, I'm going to multiply top and bottom by K. And my unit ends up being Kelvin, which is what I want. So it looks like everything is good. That gives me a number of 285.29. Checking my sig figs, 5.6. I'm thinking this is going to be 285. Looking back up here, I've got 3 sig figs here, 104. So I should have my answer to 3 sig figs, which would be 285. Which sure enough is the answer, so it checks out. Yes, units are a pain. Yes, you need to learn how to convert, how to write stuff down. No, you do not ignore units and just pretend like they aren't existing. Thank you very much for your time.